Good morning, ladies and gentlemen. Welcome you to this GNF. The topic this GNF is reusable launch of small satellites using scramjets. To be given by Professor Michael Smart. I would like to introduce Professor Michael Smart. Professor Michael Smart graduated with a Bachelor of Mechanical Engineering from University of Queensland in 1985 and obtained a Master of Engineering Science from University of Queensland in 1987. After working in engineering consultancy industry in both Australia and the UK, he completed a PhD at New York University Polytechnic in Brooklyn, New York in 1995. He then spent 10 years as a research scientist in the hypersonic air-breathing propulsion branch at NASA Langley Research Center, performing scramjet research and testing. He returned to the University of Queensland in 2005, and in 2007, he was appointed University of Queensland professor and the chair of hypersonic propulsion. Professor Michael Smart is world leader in the design of 3D scramjets. As head of University of Queensland's HiFire group, he conducts scramjet-related research within the University of Queensland Centre for Hypersonics, with particularly emphasis on flight applications. His scientific lead on flights 7 and 8 of HiFire program. And in 2012, he was awarded along with 3 colleagues from Defence Science and Technology Australia, the US Air Force, and Boeing, the International Council of Aeronautical Science von Karman Award for international cooperation in the field of aeronautics in acknowledgement of the collaborative achievements of the very successful HiFire program. Now let's warmly welcome Professor Mark Smart.
Thanks very much, Ruheng, for organising, for the introduction to me, but also for organising the session as well. I appreciate the opportunity to talk to the international audience at the IAC conference, and the conference has been a great success in Adelaide and very well organised by the committee, so I commend them on that. So today I would like to talk to you about a different way of going to space. So historically, rockets have been used to go to space from the 50s, 60s, and these beautiful rockets that are still launched today all end up in the ocean. And when you want to launch your next payload, you then have to build another beautiful, lovely rocket and then throw it in the ocean. And as an engineer, which is what is my training, I love technology and I love creating new technology, but to just launch it once and have it land in the ocean is, it's disheartening. And so from a philosophical point of view, the point of my talk, which is actually the result of a long series of research done not just by me, but by many people at the University of Queensland. We have a Centre for Hypersonics at UQ. We have about 30 people there, and we've consistently had about 30 researchers, academics, PhD students, research fellows. who have worked in the field to really try to understand how to come up with an alternative to rockets for hypersonic propulsion, and also, by implication, as a replacement for a rocket as a stage in a space launch system. And so that's really the motivation for this talk. And the great advantage of an air-breathing propulsion system like a scramjet, which I will talk about, it has tremendous fuel efficiency. ISP to rocket people, propulsion people, because it doesn't require propellant. Sorry, it doesn't require oxidizer, it requires propellant, requires fuel. So it has an advantage in that area. It has its own disadvantages as well. A scramjet engine cannot operate till it gets to about Mach 5. So it needs to be part of a staged system. And most space launch systems are staged, so it actually fits quite nicely in that paradigm. But I think the real advantage of a scramjet system or an air-breathing system is it's reusable. It's essentially an aircraft. And what we're talking about here is flying to space. So, and flying not exactly like an aeroplane, but using those ideas of lift, maneuverability, flexibility that are all part of an aircraft system, and then I'm trying to apply it in a simplified way to a space system. So I'm not talking about taking off from a runway, going to space and coming back down. Maybe one day we will do that, but this is the first step towards that, and I really believe that technology has to go in steps if you really want to make some progress. So that's what I'll talk today. What I have first up, actually, is a quaint little video that sort of, well, there's some of my words along with the video, but really shows what I'm talking about. And so I'd like to first show that. So here it is. So I'll just let it.
Here we are at Australia's new spaceport in far north Queensland. On the launch pad is the Spartan vehicle. Spartan stands for Scramjet Powered Accelerator for Reusable Technology Advancement. It's a reusable vehicle for launching small satellites into orbit. It's the second flight for Spartan this week. Today it's launching a remote sensing satellite to sun-synchronous orbit, which is 450 kilometres above the Earth. The rocket booster launches Spartan on its way north over Papua New Guinea. The first stage booster has done its job. Spartan is now at Mach 5 scramjet takeover speed. The scramjet engines now fire up, and it's on its way under its own power, flying at hypersonic speed like a plane. As Spartan accelerates, the shockwave it generates at its nose becomes stronger. Its outer skin begins to heat up to as much as 2,000 degrees Celsius. The third stage rocket and the satellite are nestled on its back, protected from the hypersonic environment. Spartan has now reached its maximum speed of Mach 12. The final stage rocket fires and pulls away. This small rocket takes the satellite up to its final orbit. Spartan has done its job and can turn around to glide back to its launch site. It lands on a normal runway just next to its launch site. After refuel, it'll be ready for its next flight.
Okay, so that's a little video that was made by the communications department at UQ, but it really encapsulates what we're talking about and what we're trying to accomplish with this scramjet technology. So just what I'll talk about in the presentation, to develop any technology, you need a commercial imperative. And the commercial imperative that's out there at the moment is the restriction in the launch of small satellites. That capacity restrictions that's there, and it's been described in multiple sessions throughout the conference today. That's the commercial imperative. Sun-synchronous orbit is an important orbit for the small satellite market. So the system I'll talk about is based around supplying a satellite to that. I'll talk about the Spartan vehicle a little bit. Anyone who's interested in more technical details about it can come and see me. That we have lots of papers and other things. But you know, the real point of this talk is to get this idea across about flying to space and even just thinking about flying to space. And then I'd like to talk about the commercialisation aspects, because myself with a couple of industry partners, we formed a startup company called Hypersonics, and you know, this is sort of we're introducing that to the community here. So that's sort of the basis for my talk. And after the talk, there's plenty of time for Q&A, and Rehan will be the chairman for all that. So I won't spend too much time on the opportunity aspects, because we all know them. But you know, high-powered, high-performance satellites nowadays have shrunk in size by orders of magnitude, and it's all to do with the technology that's in our iPhones, okay, being applied by scientists to collect data, to collect information from remote sensing and supply communications, so many, many applications. And so there's a very, very strong market that's developed for satellites that are less than perhaps 200 kilograms. So that's the opportunity that's out there. And the solution that we're putting forward at the University of Queensland is based on significant research that's been funded by the Australian government and also the Queensland state government over many, many years. And we believe that we're positioned to supply dedicated launch to the market for basically half the price of expendable systems. And it's all because we're planning to reuse our system. And we're planning to use aerodynamics to reuse our system. And this Spartan system, which there's a lovely picture there showing it at manoeuvring at hypersonic speed. You know, that reusable system, you know, could be flown once a week, and you know, you don't have to build another one every time. You may have to do some refurbishment of it. Obviously, that's the case, and you know, technology can then develop from there. But you don't have to throw it away every time. So you can actually spend a good amount of money, investment up front, developing a high-performance vehicle that you can then use 10 times, maybe even 20 times before you need to make a new one. And that's the commercial aspect of this that's so important. Okay, yeah, so, and it's, you know, Australia has made a significant investment in this scramjet technology, and all of us in the community would just love to see it lead to a commercial outcome for the country. So just some studies that have been done on the satellite market. I'm sure most of the audience have seen these. So this was done it's done in 2005. I was worried it would be out of date, but it's actually quite consistent with some more recent estimates that have come through, where the number of small satellites to be launched was estimated by 2020 to be about 500 a year. This survey was actually for satellites less than 50 kilograms. You know, if you also include satellites up to 100, 150 kilos, then it's much, much more. So, when I talked about this over many years, this was always an issue. But nowadays, no one even questions the fact that there's a real need out there for dedicated launch. And what satellite operators, manufacturers do now, of course, is they use a rideshare system. So they tag along with another launch. And, you know, I'm sure the audience knows this. If you tag along with another launch, guess what? You go when and where that other launch wants to go, that big customer, and you just have to accept that. And so you try to choose, obviously, a big launch that goes to somewhere close to where you want to go, but it's very restrictive for the community. It's also quite expensive per kilogram, so the going rate, these numbers I collected about a year or so ago, but between 30 and 60,000 US dollars per kilogram for small payloads, going to sun-synchronous orbit, which is obviously a much harder orbit to get to than a equatorial orbit. And so if you add up the numbers for a 100 kilo satellite, it comes to almost $6 million is the current price. And so based on the technology that we've developed and the system we've put together, we've done some business modelling of it. We believe that this system, because it's reusable, that's the only reason that this can be done, is that we believe we can do it for half the going price that's out there right now. So what does the system look like? So I'll give you a few more details. So in the video there, it's slightly out of date. We've since done a lot of work on looking at reusing the booster. The booster is quite a large piece of kit, and it's important to reuse that, as SpaceX have done. Our solution is an aerodynamic solution rather than a rocket-based solution, and I'll show a bit more detail about it. But essentially, we're planning to reuse the boosters at least 10 times. They will require some refurbishment, and we're going to fly them back to base, and I'll show you how we intend to do that. The second stage Scramjet vehicle is basically a hypersonic aircraft. It can maneuver, it can turn around and fly back, it can land unpowered. You know, it's sort of, it's very flexible, and it's sort of the core of the whole system. And then, of course, going from Mark 10 up to orbit, you need a rocket motor, and so a small rocket motor system to take you up the last stage. And that, of course, is expendable. And that whole system, about 80% of it, of the mass, is reusable. And the Spartan name is sort of an acronym, but it's a made-up acronym. But it's one that we've found sticks in people's minds, so that's what we call it, is our Spartan system. And so the sizing that we're going for is the order of 100 to 150 kilos to sun-synchronous orbit. Okay, and so this is the flight schedule. So we use a vertical launch, so fairly traditional vertical launch. Our stack's quite high when you compare it to a rocket stack, just because, you know, this hypersonic vehicle is quite slender and sharp. But we have a vertical launch. Our booster takes us up to Mach 5 at quite a low altitude. So the scramjet has to stay in the atmosphere to operate. So our staging is done at about 25 kilometres altitude, as opposed to typical typical rocket staging, which is done at 50 kilos, because they've basically gone right up out of the atmosphere as soon as they can, because to a rocket motor system, air is the enemy. For our system, air is sometimes the enemy and sometimes it's the saviour of our system. Okay, and so we use it when it helps us, essentially. So once that booster has done its job, the intention is that it would do a re-entry and slow way down in speed. It's quite a complex re-entry. There's a lot of control aspects that we've worked hard on, and one of our students, Joe Chai, gave a great presentation on this on Tuesday. We re-enter. Once we're at low speed, we deploy this very low speed wing. It's basically a glider wing. And we deploy also a small propeller motor at the front of the booster, which is it's a standard motor that's used in the gliding industry, so no new technology. And the thing about this system is, once the propellant is expended in a rocket, you're basically left with 10% of your mass. So it's a big can, aluminium can. And so it doesn't require a lot of lift, doesn't require a lot of power to bring it home. It's just a matter of flying it like a sort of an ugly light aircraft, which is what it is. And that's what we've done, and we've actually done a few subscale flight tests of that in our group. So once the booster's done its job, the scramjet accelerates from Mach 5 to Mach 10. The upper stage is protected from the hypersonic environment. It's very, very important. There's a lot of thought that was put into the way of doing the staging. And we found the most effective way to do the staging is basically to fire the rocket off the back of our aircraft. And then that upper stage has a small rocket motor system which needs to be restarted numerous times, just like any upper stage. And so that's pretty standard technology. And that is the expendable part. And actually that part drives a lot of the costing of the system. That part that's only doing the last little bit drives a lot of the costing because you have to throw it away. All right, and just to reiterate, SpaceX do that fantastic re-entry that they do where they land a pencil on a platform out in the middle of the ocean. Sorry, a 50-metre high pencil, which is very, very impressive. That's the first stage booster. We're bringing back our first stage booster with an aerodynamic solution, but we're also going one step further. We're trying to bring back the second stage as well, and we're using our Scramjet technology. So sun synchronous orbit, so it's basically essentially a polar orbit. You don't get any help from the spinning of the Earth, so it requires more energy to place something in polar orbit. And so we've done a bit of looking at where we would launch such a system in Australia. In Queensland, we've looked at a place called Hervey Bay. And I've shown there a possible trajectory launching north from Hervey Bay. You'll notice there's some angles associated with that. That's because our scramjet, once it's flying, we can actually change the orbital plane relatively easily just using manoeuvrability of the aircraft. And so it gives us a lot of flexibility that you just don't have in a rocket system. And these ideas of flexibility have really not been fleshed out or thought through by government or industry when they think about these types of systems. And I wouldn't say that we've fleshed it out completely either, but we've found a way that we think makes a lot of sense. Another possible launch site, actually a very effective launch site, would be on the south coast of South Australia and just launch directly south. And in fact, you'd have a large angular range that you could use for that. So that is definitely an alternative to the Queensland site. Okay, so I talked about the first stage booster. So we've done some subscale flight testing. We really didn't know how this thing would fly. It's very ugly. As an aerodynamicist, it's an ugly duckling. It really is. But we've worked very closely with a small UAV company called Australian Droid and Robot, and they basically make UAVs and fly them. This was about the size that they normally fly. This is like a quarter scale. It has a wingspan of about 4 metres or so. And between us, we developed this, it's essentially a UAV, it's radio controlled, it's piloted from the ground. And we've done some flight testing of this thing. Just taking it off and flying it around, making sure we could generate enough lift and it was manoeuvrable. And lo and behold, it actually flew no problem. Because this thing is just so light, you know, it doesn't need a lot of wing to help it to fly. And so that's been really interesting to learn how to do that. We've done 2 flight tests. There actually are videos of the flight tests up on the internet. There's a link there, but you can search the link as well, so you can see some of the flights that we've done. And so so we've called this the Australian Flyback Booster. It has to do a hypersonic re-entry without the wings deployed. So it's essentially a cylinder with some like all-moving fins on the back, and it does have to go through quite a complex manoeuvre to re-enter, and that's one of the aspects of the system that we're really going to work on in the near term, about proving that we can do that by using a balloon drop system. You know, the system flies back to base with the propeller, and hopefully there'll be minimum maintenance. There will probably be a little bit of maintenance in the rocket motor system, but in terms of the flyback system, it's just a light aircraft, and we're hoping that we won't have much to do. Now, you might ask, where's the rocket motor coming from? So in Australia, we really don't have any experience or history in designing, making rocket motors, particularly fluid propellants, rocket motors. And so we've been in conversations with a number of US suppliers of that rocket motor. So we don't want to, we're an expert in scramjet technology, hypersonics. We want to work with people who are experts in their area and collaborate to make this thing happen. So we're not planning to make and design our own rocket motor system. I've been talking to many people here at the conference this week about possibilities for that, and there are lots of possibilities out there. And yes, so that's been a really fun aspect of the whole system, is learning about how to fly the flyback booster. So you know, the hypersonic vehicle is Spartan, so it's got 4 Scramjet engines on it. These engines are quite highly developed. They have to accelerate from Mach 5 to Mach 10, and we have no moving parts in them. And that's the technology that we've spent the $100 million or so of Australian government funding learning how to do. And we know how to do that. And we want to make use of it. Okay, so that's where that knowledge has come from. It's been an ongoing investment over a long period of time in experimental facilities, in PhD topics, in flight programs, the HiFire program, which I'll talk about in a sec, all those things have contributed to us being able to develop a system that can really function out there in the real world. And of course, this thing can fly back unpowered. It's actually quite a high LOD aircraft, much more manoeuvrable and flyable than the space shuttle, which came into land unpowered as well. Okay, and so, yeah, so this whole idea of reusability, we're following on from the great work that's been done by SpaceX and really waking up everyone's eyes to this idea of reusability, but we're able to take it a step further because of our knowledge in this Scramjet technology. Okay, so I mentioned HiFire. So I've had the pleasure to be involved in a flight program that's been managed by the Defence Science and Technology Group in joint organisation with the US Air Force. And both UQ and Boeing have been partners since the inception of the whole program. Boeing have been very involved, and UQ have as well. And our team just works so well together. This combination of the university, the industry, and the governments. We basically worked as one big team, and it was really amazing that we were able to do that. And hopefully, there's going to be further projects, not just in this area, but in Australia, where the three types of organisations can work effectively together to really move technology along quickly, because technology has to move quickly. Otherwise, the reason for you developing that technology is gone by the time you finish it. And so, if we spend our time squabbling between the industry people, the university people, and government, and how do we do that, 5 years go by and we've accomplished nothing. So. HiFire maybe doesn't work in all situations, but it was a really effective way to do this. Okay, so I've shown two of the models there. The one on the top is a Scramjet engine, EQ Scramjet, hydrogen fuel. We flew it in 2015. The one on the lower was sort of the pièce de résistance for the whole program, which was HiFire 8. We have not flown that yet, and yeah, we haven't flown it yet, so I'm not sure where we are with that at the moment, but hopefully that will get flown at some point. Anyway, but the main thing about the HiFire program, or one of the main things, is we learned a lot about flying stuff. And so if we're going to develop this technology, we're going to have to fly that Spartan vehicle numerous times and learn about it and fly it back. And the development of the technology will have a significant flight component to it. And all this knowledge that we've gained, and HiFire, both UQ, and DST, and also Boeing, is really going to help us. And BAE Systems were also heavily involved in the later flights of HiFire, which was a fantastic thing as well. All right. So the main goal of that HiFire was to develop hypersonic technology for many different applications, and Spartan is one of those applications. All right, so flying to space, a new way. So I've sort of talked philosophically a bit about this, but I wanted to just stop in the middle of my talk and really just re-emphasize that. We're talking about trying to use lift in a useful way in a space system, space launch system, and really think about it. And I'm sure there are many ways to use lift in a space launch system. This is the one that works for us because we have our Scramjet technology. But I think the whole community, when we're thinking about reusability, is not just to think about a rocket system to help us with reusability. Think about flying something. Use the atmosphere. Pay the price in thermal protection if you need to. But I'd love to see more open sort of ideas floated, trying to do this. So yeah, so flying to space, a new way, I think. Would be a really interesting thing for the community to take on. And and it's about flexibility. So rockets, you point them, you fire them, and they're going to go that way unless something goes wrong. There's so much more flexibility associated with aircraft systems, manoeuvring, the timing, the throttling. There's so many aspects that really haven't been thought about in a deep way yet. All right, so There are some commercial players already in the market, and I just wanted to, some of them may be in the audience, so I just wanted to give a quick assessment of them from my perspective. Please ask questions about my perspective if you see fit. So I've just talked about two. They're the two serious ones that I see. So Virgin Orbit are doing great work in Long Beach, and of course Rocket Lab in New Zealand doing fantastic stuff, and they had their first flight this year, which, like, from my perspective, if I was doing that, I'd be so happy with the success that they had. They didn't quite get to orbit, but that'll be the next flight, so they've done extremely well. So, talking about technology though, both those companies are using fully expendable systems, so they're still tossing everything away. They developed their own LOX kerosene motors. Obviously, for sizing reasons, they needed a motor of the correct size for them. And the expendable business model is about making lots of rockets as cheaply as you can. And as we all know as engineers, making things as cheaply as you can, there's this question of reliability, right? And those ideas really fight against each other at a base engineering level. And so you need to manage those, and that's what's really important in an expendable system. And obviously, if you're throwing away the rocket every time, if it costs you an extra $1 million for that rocket each flight, that's bad. So it's about vehicle cost. The vehicle costs are very sensitive. You know, any business model that you do, you'll see that. In terms of launch methods, so Virgin Orbit are using an interesting air launch system, provides a lot of flexibility. As I've mentioned about using lift in other aspects of the system. However, I'm not sure the mixing pilots and having a rocket on the wing is necessarily a commercial way to go. I don't know with the Virgin Orbit people have dealt with that, but in my time when I worked at NASA, mixing men or women and rocket propellant, turbo pumps, all that sort of stuff is a complex mix, and the safety people get very nervous about things like that. And of course, Rocket Lab are doing a very conventional vertical launch. All right. Yeah, and so yes, to make a point, and everyone knows this, SpaceX are not in this market. They went for the much bigger systems, of course, so that gives us all the chance to try to do something without SpaceX beating us all to it. So just a bit more detail. So this is all information I've gathered from the web, so if it's not accurate, I don't claim to have checked it out. This is just straight out of Google, right? So Virgin Orbit, they've gone for a bigger payloads, 200 kilograms to sun-synchronous orbit. I think their price is like 10 million US, so it's 50,000 a kilogram. The manufacturing facility is in Long Beach, and they launch from Mojave or other places. And the figure that I've shown here is not mine, it's from The Economist magazine. It was actually a beautiful figure, and so I have used it and I have given reference to it. But it just shows all these different systems side by side. So the bigger systems, more traditional ones, and then these little ones. And as you can see, these little rockets, they're little. I think the Rocket Lab one is 16 metres in height. And so Rocket Lab have gone for a smaller payload, 100 kilos to sun-synchronous, so half the price in total, but the same price per kilogram. And of course, they manufacture and launch in New Zealand, but they are a US company. And so if we put Spartan on here, that's pretty much what it would look like. So it's quite a high, long stack, and that's just because of the nature of the hypersonic vehicle. Okay. All right, so if we're going to invest money in this new type of system, how are we going to stay ahead of competitors, possible competitors, to make sure that we can end up with our commercial outcome? So we need to think about what is the difference of this system compared to others. So the obvious one is reusability, so all other systems are throwaway. I've already mentioned some of these points here about this issue with reliability when you're trying to make things really cheap. you know, because our system is reusable and we can use it many times over, it's much less susceptible to vehicle costs. You can spend a lot more money on your vehicle if you're not going to throw it away every time. You know, that's obvious, but you know, it needs to be stressed. There's a lot of resistance, I think, to making reusable vehicles because they're so expensive. But I mean, you've got to just put it into a business model, and you can see the numbers just jump out at you. Even if your system is relatively expensive to make, if you can use it 10, 20 times, well, the numbers are just there. You don't need to be a rocket scientist to work them out, right? Okay, so they're differentiators. What about a competitive advantage? So the competitive advantage is that based on our business modelling, we can operate the system for half the price, the going price of the other guys, and still make a hell of a lot of money. And, you know, these things need to be fleshed out, but I mean, this is our initial assessment of the system. And, you know, this is based on the business modelling that's been done by my industry collaborators. It's not been done by me as a university person. So this, you know, they've really had a good look at it, and they believe that that these numbers all stand up. Okay, the other aspect about differentiation is, you know, how sustainable is this technology? Can someone just go and spend a couple of million and catch up with the Scramjet? Well, in this case, you can't. That Scramjet has really been the product of tens of millions of dollars of research. And even if you started again now, it would still take you that. And so, yeah, there's a real large barrier to other players coming in to the market in the Scramjet side. So, and also, just another point, you know, when we talk about Australia developing a launch system, we're not talking about the space shuttle system or the Apollo, we're talking about a relatively small thing, which can be developed for, you know, of the order of $150 million. Like, it's not a $3 billion program. And I think people in government get a bit scared when we say, oh, we're going to launch stuff from Australia, we're going to have a space shuttle or something. But that's not what this is. That is not the modern thing. Modern things are small systems and much, much cheaper and can just be operated on a commercial basis. All right, so speaking of commercialisation, so my collaborators and I have recently formed a startup company. It's called Hypersonics. And, you know, this is sort of my first opportunity to introduce it to the audience. It's a collaboration between UQ, BMT WBM, which is an Australian high-tech company. Dr. Russ Morrison, one of the leaders of BMT WBM, is here in the audience if you want to have a chat to him. And so is one of the staff members. So, you know, this whole idea has grown out of the university, but it's time to bring it out into the industry. And so that's what this is all about. And we've also got as a partner, a collaborator, Australian Droid and Robot, who developed the models for the flyback booster testing. So that's our collaboration. We're just getting started and talking to people about how to fund this and how to put it all together. So watch this space, I hope. And of course, other partners are welcome too. Obviously, we're talking to rocket people, but other partners are certainly welcome. And, you know, we'd like to see this technology, which Australia has invested in significantly, prove itself in the marketplace as something valuable. All right, I think I'm pretty much at the end. Yeah, so just some takeaways, and then we can have some Q&A. You know, Scramjets, they do have the potential to really contribute to this small satellite launch community. This three-stage system that we're talking about is 80% reusable, and that's why it makes commercial sense. And there's also these aspects of flexibility that, you know, have really not been thought through. The opportunities have not been thought through. And based on our knowledge of the system, we believe that supplying a system for half the current rate is very viable. And, you know, this system we've talked about in terms of a commercial market, but there's also the opportunity to supply a responsive space for Australian defence as well. So I think that's all I have to say, Rihang. So thank you.
Thank you very much, Professor Mark Smart, for your very interesting topic. Now we have about 15 minutes time for questions.
Will you manage the questions?
Yeah, okay. Yes, okay.
I think there's a guy.
Okay.
Hi, thank you for your talk. My question is, what is the maximum number of flights you expect the flyback booster and the Scramjet to be able to have in its lifetime? And actually, sorry, I have two questions. And the other question is, do you intend to, sometime in the future, try to make the third stage also reusable? And indeed, is it even possible? Yep. Thank you.
Okay, good question. So I'll answer the first one in two ways. So when we think about doing the commercial side of things, we have to say, well, how many times do we think we can reuse it? And we've tried to be conservative. We've said 10 times. So in our business modelling, we've assumed that we're going to throw it away after 10 uses. But in reality, I think as we learn how to use the system, particularly the Scramjet system, I think we'll be able to fly it a lot more than that. So that's the answer to the first question. So we think we should be able to fly it a lot more than 10 once we get to understand how it works. And the third stage, I haven't done a lot of thought on how to bring that back. You know, it's going very, very fast. And to re-enter something that fast, you need quite a substantial thermal protection system. And so we haven't done a lot of thought about the third stage. Oh, there's a question.
Okay, a question. Yeah, over there. Yeah.
My question was, for such a complex design, and I'm sure there's a lot of work that has been gone through, I just wanted to know, one was how much was the students' involvement, your undergrad or graduate level within the university, and are you guys open for other universities to collaborate with you as a learning experience for other students, and as well as partnerships that you guys may be looking for?
Yes, so we are a university, and so we run slave labour camps called PhD students. So that's how we've developed the technology, by students. That's how we do it. That's how we've done it. That's the academic model, and it really works. Like, for example, our Scramjet test facility is operated by the students. Now, when I say that, everyone thinks, oh, well, it's operated by the PhD students, not undergraduate students. But these are highly trained mechanical engineers. So why not use them? Because they learn a hell of a lot by operating our facility. And when they come in and do an experiment, they understand how the facility works, and then they can concentrate on the experiment. So yes, PhD students have been significantly, and continue to be significantly involved in the research. Now, in terms of partnerships, we've always had, the hypersonics community is a very international community. We've always had close collaborations with many different countries, and we've developed many, many friendships all over the world doing this. So we're very open to that. Obviously, some of the more applied technology is not open to general research, but that's not where the research needs to be done anyway. That's more development. So there's still plenty of fundamental questions in the hypersonic regime which are of interest, and yes. So we are open to collaboration, definitely.
Yeah. Professor, my name's Richard Tonkin. Thank you very much for your talk. Do you see the new Australian Space Agency as being able to assist in facilitating what you're doing, and particularly with regard to some funding?
Well, yeah, I'd like that to be the case, but we need to justify that to them. What I hope, and what I'm sure many of us hope, is that the space agency has its own budget that it can apply to bring niche technologies that Australia has an advantage in over the rest of the world, and can bring those along that can then flow into economic benefits for the country. So I really hope that that's where the space agency ends up. And I'm sure that's the intention to do that. So definitely, I would hope that if we can convince people at the agency that this is a valid way and something that Australia would like, that should do, given its investment so far, then yes, I hope so.
Okay. Thank you, Professor. And okay. And you in this lecture, you just talk about the Scramjet, and it's a kind of air-breathing engine. And recently, such as rocket-based combined cycle and turbo-based combined cycle are also air-breathing engines and used on the reusable launch system. And my question is that which kind of engine is a better choice for the reusable launcher vehicles, and which for the air breathing mode, and in the first stage or in the second stage, which one is a better manner? And in the lecture you just have that the reusable manner could keep a lower price for the launch system. But in our research, that if the air breathing engine used in the first stage, such as the maximum speed is Mach 5 to Mach 8, and the thermal protection could be used such as the metal-based materials, which in that case, the vehicle could fly just like commercial airplanes, and it could fly for many times. But if it used in the second stage, the vehicle, the thermal protections, it will endure the dynamic pressure just like the space shuttles. How could we be sure that it could have advantage than that kind of rocket one? Thank you.
Okay. So sort of two questions there. So there are these other air-breathing engines out there, turbine-based combined cycle, rocket-based combined cycle engines, and some of them have the capability of taking off from horizontally, right? And that is true. But what we've tried to do is just keep it simple and accept the limitations of the technology that we know. That scramjet, there is no moving parts in that scramjet. There's no turbine, there's no rocket motor, no turbo pump, there's nothing. And so we're sort of accepting that limitation on ourselves to try to move the technology along. And so more complex systems that can take off from the ground, maybe they're the next phase of using air breathing for space. But for us, I've worked in the hypersonic community for many years, and we still don't have a scramjet that's out there flying and doing anything useful. And so that's my goal, is to make that happen. The second one you asked about is thermal protection. So if we're flying at Mach 10, that vehicle will be manufactured out of high temperature composite materials. That's really the only and best, it's the best solution and the only solution. And there's been significant achievements in the ability to make unusual shapes in those materials over the last 10 years or so. So we're reliant on that technology, and we have collaborators who we're working with who can supply that technology to us. So that's the second answer. Yes?
For your flyback booster, was there any reason why you chose a conventional wing over a lifting body design? It's for drag. So a lifting body creates a lot of drag. And so at Mach 10, we've got thrust from our engine and we have drag from our vehicle, and we need to have more thrust and drag. So we need to have a very low drag vehicle. So that's why we've gone for that system. The other possible shape would be like a wave rider shape. But what we found was that for space access, where you're just trying to accelerate as quickly as possible, lift is not so important. What's important is net ISP, so low drag. So that's the rationale for the you know, that vehicle has quite small wings. The wing size is actually set by the ability to land. It's not set by the amount of wing that we need when we're accelerating, actually.
Professor, thank you for your presentation this morning. It's fantastic to see that Australia is doing something exciting in the space industry like this. As an enthusiastic Australian with regard to space, I'd like to see this kind of thing commercialized tomorrow. When will you start launching commercial payloads? What is your vision for the next 10 years of your company? And can this kind of system be scaled for human spaceflight? Thank you.
Yeah, so we have a plan, a business plan, and it's sort of, it has 3 phases, like an initial phase where we put the team together to make it happen. I don't like to put dollars on things, but, you know, 5 to 10 million sort of dollars, and then a intensive flight testing phase, which would prove the technology. And then there's also quite a bit of effort to take that prototype technology and then to commercial. And we believe that with the funding that we need, that we could do it in a 6 to 7 year period. So 6 to 7 years, we could be launching commercial. So that's the sort of time scale that we're talking about. What was the second thing you said? Well, yeah, I suppose that's it, yeah. So in 10 years' time from now, we'd be flying from somewhere in Australia once a week and really, you know, and contributing to the community, to the space community, because they need to be able to get launches up there, but also, you know, doing it for Australian defence as well, for any capability they may need. So.
2 questions on my side. Fabrice Cheny from Airbus Defence and Space.
Yes.
First one, fundraising. How much money to start operating, basically? You said 5-10 millions for the first phase. What about the step number 2 and step number 3? And second question, which regards the, let's say, the targeted market. You say you target 150 kilograms to SSO. So first of all, what altitude in SSO? Because you know, we could debate on this. And second, do you think that are you sure that 150 kilograms in SSO is really the core of the market for the years to come? Thanks.
Yes. So the other systems that are out there, one has set their size at 100, one at 200. I think as time goes on, I think the required mass of satellites will decrease, but not astronomically as it's done over the last number of years. We've looked at different sizing. We believe 150 is about right for SSO, but it's all based on looking at the customers that our competitors essentially are taking on. So, you know, that's the reason for our assessment. The other thing is that there is a scaling issue that goes on. If you try to go too small, your structural weights just start to beat you. And I think going down, you know, to the 50 kilos, 20 kilos, you know, 20 kilos different is your payload, but I mean, if your propulsion system doesn't work quite right, then you might have negative payload. So I think going below 100, I think is, for one of these systems, is probably, you need to really understand your system extremely well to be confident of that. In terms of the funding, so Russ Morrison is sitting beside you there. He can tell you, but like, of the order of $150 million, we believe is the full up, with that much money, and a 5 to 7 year period, we could be launching. That's our assessment right now. And we've been conservative. No, US dollars. Yeah. No, we always talk in US dollars, right?
Thank you, Professor, for your impressive presentation on this new model of this reusable launcher. Two questions. First is, what's the proprietary duration at the launch pad for the whole system? I mean, all of these stages integrated together. And then...
Sorry, what do you mean by that?
Preparation duration at the launch pad, I mean operationally, and also the corresponding, let's say, logistics issues you have foreseen currently.
Okay, so we would hope that turnaround times of the order of a week is easily possible. And, you know, there are obviously some logistics associated with our stack. Our stack is quite tall, as I indicated, for the size. I think there are some, you know, handling things that will be very important to make quick turnarounds available. But we're hoping that particularly the booster, we'll just have to refuel the thing. Fill it full of LOX, fill it full of kerosene again, and then it should be ready. There may be a little bit of refurbishment of the rocket nozzle. We've been looking at different aspects of that. So maybe maybe there's a bit of work to do on the rocket nozzle. In terms of the Scramjet vehicle, it's an aircraft, so we're hoping that once it lands, check it out, and just refuel it again. You know, this whole idea of just being able to refuel a system, check it out again, I think it really helps with the turnaround time. So we're hoping a week preparation.
So that's including the proprietary duration for the launch and also for the maintenance, you mean?
Yes.
Okay. And the second one is that you see for this, let's say, for the launch pad and also the re-entry, let's say the returnable site for the first and the second stages, are they the same or are they separately located? And what's your target of the management, let's say, cost for cooperating all of these management?
Yeah, so we definitely need, obviously we need a runway near the launch site, but particularly the flyback booster is very light. It doesn't require a long runway at all, like much smaller than a small airfield. The Scramjet has more stringent requirements on the landing, but it's not substantial. Just a fairly typical airfield runway, and then have a hangar beside it, and roll it into the hangar, do the work you need, and then take it out to the pad. So we're hoping that a lot of those activities are really more like aircraft than rockets.
Okay, one more question, please.
Hi, Professor Smart. Thank you for the talk. Hypersonic technology is really quite fascinating. I had some questions regarding the cost. I'm going to narrow it down to one. With some of the big players looking to move into the small sat launch market, we've got Blue Origin are hoping to launch very soon for low Earth orbit. Virgin Orbit are going to launch soon. SpaceX are already launching, obviously, much larger payloads. Ride-sharing is not the most economical or effective way to get into orbit, but the cost to orbit is considerably less. And I was hoping to get your thoughts on why we can discount these as threats to the technology for something that's not launched for potentially 6 or 7 years compared to companies that are launching currently or in the next year or two.
Yeah, no, that's a good question. So, in terms of timing, we're behind a bit compared to Rocket Lab and Virgin Orbit. But you mentioned the cost of rideshare. Those numbers I showed there, like $50,000 a kilo, that's the rideshare cost. So the sort of prices that have been quoted by the expendable systems are pretty much the same as rideshare. But what they supply to the customer is the exact orbit, the exact timing, the exact schedule that they want. That's the extra thing that's being offered for the same price. And those things are absolutely important to commercial companies that want to supply a service to their customers. So we are behind. in timing, but we're hoping to be able to supply a service at half the price. So I think that would be my argument to say, even though we are behind in timing, we're hopefully going to supply a cheaper service when we get there. But also, I think there's room for all the players in the market. There's no dedicated launch system right now. There's the order of 500, 700 satellites every year that are supposed to fly. There's plenty of space in the marketplace for numerous players, and so I don't see that as a real issue at this stage anyway. Yep.
Okay, thank you. Due to the time limitation, we are finishing this GNF. I'm sure you have more questions to ask. I suggest that you could talk and discuss the topics with Professor Michael Smart later on. Thank you very much, Professor Michael Smart, for your very interesting talk. Yeah, thank you again. And also, thank you for all audience for participating in this GNF. Thank you again. Okay.